morning. Welcome back to the lecture on rapid manufacturing costs or costing in rapid manufacturing. So, we have discussed the machine, labor and material costs in the previous lecture. So, machine cost was discussed. Machine is capital equipment at the cost of purchasing the machine and cost of maintenance. Then we had material costs, then we had labor cost. Typically, when I say machine plus material plus labor is the total cost of the product. So, in general these ranges can be broken down into certain percentages. I can say machine cost is from 50 to 75% the cost of the equipment, then material cost is from 20 to 40% and labor cost is from 5 to 30%. It all depends upon the type of application and the type of skill that is required and the kind of material that we are using. So, this is the typical breakdown. So, next we have cost estimation models. The cost model, broadly speaking, cost falls into the four main categories that we have discussed. Number one is machine purchase, second is machine operation, third is material, fourth one is labor costs. And the total cost is purchase cost plus operation cost plus material cost plus labor cost, and also cost per unit per part basis, for which we had the illustration that I showed you in the previous slide. This is per unit cost. So, this is calculated by dividing by the number of parts, the total cost by number of parts by n. So, this P is actually P by n, this is O by n, this lowercase letters are the capital case letters divided by the number of parts. This is equal to L by n. What is purchase price? This is one of the models. There are certain models which are developed by additive manufacturing people who are working in the analytics or the calculation of the costs in additive manufacturing. This is only one of those models that I am discussing here. However, certain complex models are there in the market, but to understand the basics or the simple model of additive manufacturing, this is well enough. So, purchase price for one build can be calculated using this formula, that is purchase price. I am talking about 1 unit now, that is the total purchase price into TB by 0.95 into 24 into 365 into y is years. This 24 into 365 represents the number of hours in an year, and TB is the time that is taken to make a build. You might recall the time that we took to manufacture the 3D print was around 4 hours in the laboratory demonstrations. So, this is that time for the build in hours. Then operation cost is simply the build time multiply the cost rate of the machine, which can be complicated function of machine maintenance, utility costs, cost of factory floor space, company overhead, where operation cost is denoted by CO. So, this operation cost is the build time into the operation cost rate per unit time. CO is cost per unit time and this is time, it is build time. So, next is material cost. Material cost is conceptually simple to determine. It is the volume V of the part multiply the cost of the material per unit mass. This is cost per unit mass, this is volume, this is cost per unit mass, this is density or specific gravity or mass density, N is the number of units. What is KR and KS? This we will discuss. So, this material cost has a complex dependency on the recyclability of the material used. For instance, for powder processes where the build material is not 100% recyclable, the fraction of the build volume made up of parts versus loose powder and the powder capture the efficiency of the process. Now, the term KR will be introduced for the purpose of modeling the additional material consumption that consider these factors. What are these factors? The recyclability or 100% consumption. This is questioned. Okay. In addition, for processes that require support material such as fuse deposition modeling and stereolithography, the volume and the cost of the supports need to create each part also must be taken into account. Factor Ks takes into account such processes. Typical values of Ks varies from 1.1 to 1.5 to include extra material volume that is needed for supports. So this is for supports, this is for recyclability or the utilization of the material or the consumption of the material. We have this factor Ks, S is for support and this is Kr, R is for recyclability, right. So this gives us the material cost. So it is simple to determine if we just use these factors, that is around 10% of extra material would be taken, around this means around 50% of extra material will be taken for supports. But exact measurement or exact model or exact factor values are to be determined using some experimentation or from past experience or from the experts, those can be known. Next is labor cost. Labor cost is the time required for the workers to set up the build, remove fabricated parts, clean the parts, clean the machine, get the machine ready for next build. This is the total labor cost. So setting up, then removing and taking the part off. This is pre-processing. This is post-processing. So labor cost is directly T1 into C1, the time taken and the cost, that is the wage rate for the specific worker. Next is build time model, that is TB. You might have seen that we have all the factors here. Purchase price is the price that is spent. TB is one of the factors that is coming in purchase and operation cost. Labor and material costs can be determined from these models, M model and L model. So the P and O model, P and O has this factor build time TB. Now what is this TB dependent upon? So it is an additive function of three factors, TS, TR and TE. TS is deposition time, TR is recoat time and TE is delay time. The major variable in this cost model is the build time of the parts. Build time is a function of part size, part shape, number of parts in the build and the machine's build speed. These three different times are added to get the total build time, deposition time, recoat time and delay time. For this analysis, it will assume that the part size is in the term of its volume and its bounding box aligned with the coordinate axes, that is BBX, BBY and BBZ, three different axes. Recoat time is easiest to deal with. What is recoat time? The processes that build in material beds or vats have to recoat or deposit more material between layers. Other processes do not need the recoat or they have TR is equal to 0. So recoat time for building support structures can be different than times for recoating when building parts as indicated by this recoat time. Recoat time TR is equal to LS into TRS plus the second factor here LP into TRP. So what is LS? LS is the number of layers. TRS is the time to recoat a layer of support structures. So this is number of layers and time to recoat a layer. LP is the number of layers for building part. That is LP is equal to BBZ Z direction by LT. TRP is the recoat time for a part layer. For a part layer, not a specific layer. So TRS is the time to recoat a layer. So essentially this LT is the layer thickness, this is L small t, this is layer thickness, it is mentioned here. So, this is essentially telling us that recoat time is divided into two factors, one is support recoat, a second is part recoat. LS and LP are the thicknesses of the support and the part respectively, and TRS and TRP are the time taken to recoat the layers of the support and the part respectively. So, this is TR, that is one of the element in build time model. Now, scan deposition time is a function of total cross section area for each layer, the scan or fill strategy utilized, and the number of layers. Cross section area depends upon the part volume and the number of parts. Scan deposition time, that is TS, also depends upon whether the machine has to scan vectors to build the part in the pointwise fashion, as in stereolithography and selective laser sintering, fuse deposition modeling, or the part deposits material in a wide line wise swatch, as in inkjet printing processes, as a complete layer, as in layer based photopolymerization processes. So, there are three ways. Number one is pointwise fashion, number two is in a wide or line wise fashion, and number three is complete layer. Equations are similar for these. So, we will present the build time model for scanning and leave wide swath deposition and layer based scanning processes for the exercises. So, this is a little complex model, for we cannot build models for all these three processes. So, scan deposition time is depending upon the different applications or different way in which this scan vectors work, whether point wise or line wise or layer wise maybe. The number of parts can also be computed using this relation, where these two factors are here. In the direction x, direction y, we have BBX and BBY, where PLX and PLY are the platform sizes, and in x and y directions, GX and GY are the gaps, and 20 mm terms prevent the parts from being built at the edges. So, this is 20 mm is distance from edges. Okay, this terms tell distance from edges. This analysis can be extended to 3D build chambers for the processes which enable stacking in Z direction. This is only in X and Y directions, and Z direction it is taking, it is making layer by layer, it is going in that direction. So, this is we determine the number of parts. Next term TS. TS is the scan time or deposition time. Deposition time. This is a function of scan speed and scan length. So, this is scan speed, this is scan length, SL is scan length, SS average is, this is average scan speed, average scan speed, which is a function of scan speed in x direction and scan speed in y direction. This is scan length, SL is scan length, which is a function of I will put A average, average surface area or average cross sectional area, cross sectional area. So, there are certain models to determine the scan length and average scan speed. So, I am not going into that detail, just we need to know that total time is equal to time for R recoat plus time for scan plus time for delay. So, we have determined what is TR, we have seen what is TS. This is 3600 is a factor that converts hours into seconds. This is that factor. So, next we have with us is the final term, that is TE, delay time. Many processes have delays built into their operations, such as platform move time, pre-record delay, post-record delay, nozzle cleaning, sensor calibration, temperature set point delays, that is waiting for the layer to heat or cool within a specific range, and so on. So, this is actually setup time. This is again setup. This is maintenance. So, this all is non-productive time, but this cannot be ignored and it is there, and we need to minimize this. These delays are often user specified and depend upon the build details for a particular process. So, the delay time is given by this relation LP into time for pre-delay and time for post-delay plus time for start. Additionally, some processes required a startup time, for example, to heat the build chamber or to warm up a laser. This we also explained when we discussed about 3D printing and also 3D scanning. 3D scanning, the scanners also need some startup time, and also I showed you the graph at what time does the scanner is heated up to work. It was around 3 minutes if you remember for RTX scanner. So, after that it can work properly. So, this startup time will be denoted by T start. For our purposes, delays will be given by, but it is important to realize that each process and machine may have additional or different delay terms. So, this is a generic term, but delay terms would be very different for the different processes. For example, it can be different in a way. If parts have many fine features, longer pre-coat delays may be used. If I say fine features implies longer pre-coat delays. So, this is in the case of stereolithography in general. So, this longer pre-coat delays may be used to allow the resin to cure further or to strengthen the part, for resin to cure, to strengthen the parts, because the features are very fine. So, before subjecting the fragile features to recoating stresses, this is important. These terms can have other factors or other elements that can be included in this. This is now a generic build time, that is TS plus TR plus TE. First we talked about TR, that is the recoat time, that is the recoat for support and recoat for part. Then we had our scanning or deposition time, that is a function of scan length and average speed. Then we have the delay. Delay is pre-delay plus post-delay into LP plus T start. LP, you know, it is the number of layers. So, this is the cost estimation model. We have picked a simple model to explain how the cost in additive manufacturing calculated. There are certain models, as I said, which are being developed, and the complex models. There are even stochastic models which are coming, and we can go into any detail. But to understand that what does cost estimation in rapid manufacturing has, it has machine cost, labor cost and material costs and operation costs. So, 4 costs are there. Then we had the time, the build up time, that is very important factor in that. How to measure build up time? It is having 3 elements in it. One is scanning time, then is recoat time, then is delay time. So, these all are the factors that we have seen now. One important point in rapid manufacturing I would like to touch is life cycle costing. in addition to part cost, it is important to consider the costs incurred over the lifetime of the part from both the customers and the suppliers' perspectives. For any manufactured part, not necessarily only additive manufacturing processes, life cycle costs associated with the part can be broken into 6 main categories. Number 1 is equipment cost, number 2 is material cost, number 3 is operation cost, number 4 is tooling cost, number 5 is service cost, number 6 is retirement cost. This is the total cost of ownership. One has to purchase equipment and material, then operation has to be done. While operating, the costs are incurred, electricity, etc. Then tooling is there, servicing has to happen, then retirement, with machine has to be replaced. This is also known as replacement cost. The equipment cost include the cost to purchase the machines that are used to manufacture the part. Material and operation cost, they are related to the actual manufacturing. This is actual manufacturing, right? And for the most conventional manufacturing processes, tooling is required for part fabrication. In this case, the tooling can be the tools to clean the part, to clean the machine, to take the part off, to the small tools. Okay, so those tools are there. So this may include an injection mold, stamping dies, machining fixtures in case of post processing. The other two elements are service and retirement costs. Service costs typically include the costs that are associated with repairing or replacing a part, which can include costs related to taking the product out of service, disassembling the product to gain access to the part, repairing or replacing the part, reassembling, testing of the part, inspection, preventive maintenance, all those things come in service. Then design for service guidelines indicate that parts needing frequent service should be easy to access and easy to repair and replace. So these costs are also important. The retirement cost is the final salvage value, you can say. So the life cycle costing is also important, because only the cost of purchase and operation, if it is considered, and retirement cost and service cost is not considered, sometimes it is a little expensive. Life cycle costing is a method to think about the material or the equipment or anything in which we are investing for its whole life, for its life for it would work. For instance, the life of equipment that I am going to purchase is maybe 2 years, and after 2 years I have to sell that. The overall cost, the cost of purchasing plus the material cost, that is cost of operation, that would be incurred in that. I am not considering now labor, etc. here, that is all in operation here. Operation is everything, it is material, labor, service, I am considering in all these things. So purchasing cost, cost of operation minus salvage cost I am putting, that is the resale price. So this is the total cost, total life cycle cost. So with this we have completed this presentation of life cycle costing and the costing on the rapid manufacturing parts. So what questions now you can address or you can understand from this presentation? You can answer, what do you understand by cost and price structure? This you now know. Then you can tell how to estimate design and manufacturing costs. You can talk about a model of cost estimation in rapid manufacturing. You can say how to determine life cycle costing or what are the various elements in this. So product costing part is over with this lecture. So we will meet in the next lecture where we will discuss rapid product development. Thank you.